In talking about kinematics so far in the chapter, we've been talking about movements without regard to the forces that move them. Finally, now in kinetics, we are going to start talking about the forces and the effects of forces on the body. So, kinetics is the branch of mechanics, and in our case, specifically biomechanics, that describes the effects of forces on the body. From the perspective of kinesiology, force can be considered a push or a pull that can produce, modify, or halt a movement. Forces provide movement and stabilization for the body. So, the interesting thing about muscle is that muscle cannot provide a pushing force. It can only provide a pulling force. So bear that in mind when we start talking more about muscle. All a muscle can do is pull. And in this section of the lecture, we're going to talk about the line of pull and how you determine the line of pull and what a muscle is going to do based on that. So we'll get more into that. So the learning objectives for this section are to be able to apply the concepts of base of support and center of gravity to the principles of stability. So I'm telling you, this is something that you do every day in the clinic. Every day you're working on people keeping their center of gravity inside their base of support so they don't fall. So it's very central to what we do. I want you to be able to describe the three classes of biomechanical levers, give examples of them in the body or other examples, and to explain their advantages and disadvantages to human muscle function. So some levers give you an advantage of motion, some give you an advantage of strength, more torque. Identifying the components of biomechanical levers and how torque and levers affect movement. So torque is rotational force, and all of our joint movements are rotational movements. So what's providing the torque is either muscles pulling on the bone or gravity pulling on the bone. So, we'll talk about how torque and levers affect movements. So this is great stuff. I hope you're all enjoying it as much as I am. I know you're thinking she's crazy. Okay, stability. So our center of gravity is the balance point of an object in which weight on all sides is equal. So most of us, or everybody, your center of gravity is about an inch below your navel, or at sacral segment number 2, S2. It's also the place where the cardinal planes of the body all intersect. So isn't that interesting? The base of support is the part of your body that's in contact with the supporting surface. And we'll do a lot of exercises in lab where we experiment with center of gravity and base of support. That is, they're fun and interesting. So there's a line of gravity, which is an imaginary vertical line that passes through the center of gravity towards the center of the earth. That's our line of gravity. So you can well imagine, if your line of gravity falls within your base of support, you can stay balanced. If your line of gravity falls outside of your base of support, you're going to fall over. So that's the principles of stability. So a lot of times, like we'll say after a stroke, people sometimes lose midline awareness. And so they have a really hard time staying up because they can't keep their line of gravity within their base of support because they don't, they lost this part of their vestibular sense and they don't know where their line of gravity is. So if you think of that, if your feet are farther apart, you have a wider base of support, it's a lot easier to keep your line of gravity inside that base of support. If your center of gravity is lower to the ground, it's way easier to keep your line of gravity inside your base of support. So the distance between the center of gravity and the base of support and the position of the line of gravity with regard to the base of support, that is going to determine your stability. So if you are unstable and you add a cane, that widens your base of support. And there are other reasons for using a cane that we'll talk about later in the hip chapter. But widens your base of support so it's easier to stay balanced. If you have a walker, that gives you an even bigger base of support. If you sit down, your center of gravity is lower and you have a big base of support. So there's a lot going on with stability and base of support. So when we look at it in terms of an inanimate object, so this is I'm going to go set this book on the shelf, and I would like it to stay there. So the center of gravity of the book is its center, where the mass on all sides is equal, just like in a person's body. So the center of gravity and the line of gravity has to remain within the base of support in order for the object to remain stable. So in the top illustration, the book is stable because its center of gravity is in the middle of the base of support. So bar earthquake or something, that book is not going to fall off the shelf. In the second level, the book is less stable because its center of gravity is near the edge of its base of support. So it's probably not going to fall off, but it's not as stable as the first one, where the center of gravity is in the middle of the base of support. In the last illustration, the book is unstable and it's already falling off the shelf because the center of gravity is outside the base of support. So having your center of gravity outside your base of support is a ticket to the floor. That's how you're going to get there. So the relationship of your center of gravity to your base of support is going to determine your stability. Makes sense, right? I hope. So with regard to body movements, forces can be classified as internal forces or external forces. So internal forces are generated from within the body. So typically that involves like active muscular contraction. That's our internal force. But you could have passive internal forces like tension generated from ligaments or muscular elongation. Those are internal forces as well. But anything that's generated by the body is an internal force. External forces are forces originating from outside the body, like gravity, any external load that you're carrying, like a bag or a dumbbell, or a physical therapist applying resistance to a movement. That's an external force. So kinetics is describing force as a push or pull that can produce, modify, or halt a movement. So internal force is generated within the body, external force outside the body. A lot of times when we're doing lever problems in this class, we're talking about the internal force is the muscle and the external force is gravity acting on the body segment. So that is really commonly what we are talking about. Torque is the rotational equivalent of force. So it's rotational force is what it is. So the amount of torque generated across a joint depends on the amount of force exerted and the distance between the force and the axis of rotation. So the distance between the force and the axis of rotation is known as the moment arm. Internal torques are generally muscle. They're internally generated. External torques are externally generated, and it's usually gravity that we're talking about. So a lot of times the little equation that's down there, you don't have to know that. It's just a lovely little equation for figuring out the external force based on the moment arm, but I'm not going to expect you to do that. I just want you to get the idea of the concept. So generally in the body, in the joints, internal force is being generated by muscles and external force is being generated by gravity. So with biomechanical levers, it has the different classes of levers have to do with the relationship between the internal force, the external force, and the axis. So forces that are our internal forces are usually caused by activating muscles, and external forces are usually caused by gravity or some other some other type of thing. But we're going to mostly be talking about gravity. When the competing forces interact through the system of bony levers, the pivot point or the axis or the fulcrum is located at the axis of rotation of our joint. So internal and external forces are converted into internal and external torques, which ultimately cause movement or rotation of the joints. So the relationship of the internal and external force to the axis are how we classify the individual levers. So there are three classes of levers: first class, second class, and third class, and they all have function in our body. So in a first class lever, you can think of it as a teeter-totter or seesaw, whatever you want to call it, where the fulcrum or the axis is located between the internal and external force. So sometimes you'll see in descriptions of biomechanical levers, the internal force is called the resistance, and the external force is called the force, um, or vice versa. We'll talk about it in all different ways. So hopefully we'll get an understanding of that. But just this is the way it's described in the book. So we'll start here and we'll move on from there. So the fulcrum between the internal and external force, the classic body biomechanical first class lever is the cranium balanced on on C1, and the gravity force, the external force, is gravity trying to pull our head down, and the internal force is our muscles trying to pull our head up, and they're teeter-tottering to keep us level on the cranium, on the occipital condyles of the cranium, balancing on C1 of the cervical spine. So we have that teeter-totter effect keeping our head level. And the reason we have that motion is because we want to keep our eyes level. We want to keep our gaze stable so we can visualize what's going on in the world. Second class levers are where the axis of rotation is located at one end of the bony lever, and the internal moment arm is longer than the external moment arm. So you can think of the second class lever as the wheelbarrow is the non-body example of it. So the axis is the wheel, the load is in the middle, and the force is at the end. So the body position second class lever example that's here is the metatarsal phalangeal joint. The first metatarsal phalangeal joint is the axis, so it's raising up on your toes. The load is the gravity coming down through your body, through your tibia, and the force is the muscle force pulling your heel up in the heel raise. So the load is in between the force and the axis. In the teeter-totter, the load and the force are on either side of the axis. And second class levers are they're the power levers. They're the ones that are giving you not a lot of motion, but a lot of strength. Third class levers is where the axis of rotation is located at one end of the bony lever, just like the second class, but the internal moment arm is closer to the axis than the external moment arm. So the example in the body is the biceps curl with the dumbbell. The external moment arm is gravity pulling the dumbbell down. The internal moment arm is the biceps pulling it up, and the attachment of the biceps is closer to the axis than the load is. So we'll talk about this over and over again, and it will make sense. And then we'll add nice little frills like gravity later on, just to make it interesting. So This is an example of two different elbow flexor muscles that have two different lever relationships. So I said that second class levers are preferential for force, third class levers are preferential for motion. So for creating more motion, many of the levers in our body are third class levers because our bodies were made to move. And so we have a lot of third class levers. A lot of when we start to talk about eccentric muscle contractions, where we're trying to slow down the pull of gravity, a lot of times it's the second class lever because we want power, we want control. So a third class lever favors motion, and a second class lever favors power. Okay, so let's come back to this slide. We'll talk about the line and pull a little bit, and then we'll come back to the biceps versus brachioradialis. So the line of pull describes the direction of muscular force. So we have an origin and an insertion for every muscle. And the muscle, if you know where the origin is and where the insertion is, where the muscle goes, um, you know what the line of pull is going to be, and you know what motion the muscle is going to create when it contracts. So in this example of shoulder flexion and extension, it's a sagittal plane movement, medial lateral axis of rotation. The line of pull, if the line of pull is posterior to the axis, you're going to get extension. If the line of pull is anterior of the axis, you're going to get flexion. So the example of a muscle that is anterior to the axis would be the long head of the biceps, which crosses the shoulder. It also crosses the elbow, but it's anterior to the axis, and when it contracts, it causes shoulder flexion. On the posterior side, the posterior deltoid is posterior to the axis. When it contracts, it causes extension. So there, for all of the different motions in the body, we can determine the muscle action that causes that motion by determining the line of pull. And we can determine the line of pull by knowing the origin and insertion of each muscle. So we know, if we know the origin and insertion of each muscle and what joint it's related to, we can determine the line of pull and what the action of the muscle is. So in an adduction motion, a frontal plane motion, if the muscle is lateral to the axis because it's an anterior posterior axis and it's in the frontal plane. So lateral motion pulls the bone laterally, and medial motion pulls the bone medially. So the middle head of the deltoid has its origin and insertion lateral to the axis, and it causes that abduction. The muscles that are causing adduction, the latissimus dorsi, for example, has its origin and insertion medial to the axis, and it pulls the bone medially. So knowing where the muscle is in relationship to the joint, where the line of pull is, tells you what motion the muscle is going to generate. So same thing with the vertical axis of rotation. An anterior or medial pull produces inward rotation or medial rotation, and a posterior or lateral pull produces rotation away from the midline or external rotation. So in the shoulder, the infraspinatus is posterior to the vertical axis of rotation. It's going to do external rotation. The pec major is anterior, and it's going to do internal rotation. It's going to help with internal rotation. So we'll talk about the individual actions of the muscles. So vectors are, they represent the magnitude and the direction of a force. So the magnitude of force is indicated by the relative length of a vector line, and the direction is indicated by an arrow. So when you combine two different vectors, you get combinations of vector forces. So this is the example they have in the book of different people pulling a load. And so in the top picture, you have more force going to the right. The load is going to move to the right. Um, in the bottom picture, you have equal forces right and left. The load's going to move pretty straight. So when we start to talk about muscle, which muscles assist which motions, muscle synergy, co-contraction, that sort of thing, that's where vectors come into it. So if you have a bigger muscle pulling one way, it can neutralize the action of a smaller muscle pulling the other way. That's really what we want to get out of vectors. So really, you can think of the body as a biological machine that rotates bony levers that are powered by muscular pulleys. Some musculoskeletal levers are designed to produce large torques, like the quadriceps. We have the patella embedded in our quadriceps tendon that increases the torque so we can produce a large force on knee extension. Very important for functional activities. Other levers are designed for producing high speeds or covering large distances, like reaching up to get something. We want to do it quickly and we want to cover a large distance. So when we talk about all the different levers, when we talk about all different muscles, we will talk about what type of lever action is happening at an individual joint.